start recording. We'll start talking about things. Let me get the screen share going so that we're all looking at the same thing. All right. Here we go. So you should be able to see the course webpage. Yes. So just a couple things I wanted to point out. I sent out an email earlier today letting you know that office hours on Friday have shifted. So Nikki is doing something else during that time, so Lexi agreed to step in on Friday and hold office hours from 2:30 to 4 at her Zoom room. On Monday, we have office hours in the afternoon and in the morning. So if you need help with homework on Monday, you should have plenty of access to the TAs in that case. And you can also email me questions as well. And yeah, that's what I was going to say about that, I think. And then homework is due on Monday night. So I will let you know when the next thing is available that you have to work on. In the meantime, we had a question about GLM residuals. So I thought that that might be a useful thing to go back over in the context of trying to help with homework. So I've pulled up Lecture 2, Slide 27, which talks about residuals under the context of either an empty model with no predictors or a model that has a single predictor included. So if we, let me see here. Yeah, I think I'll just keep it out of the thing here. It's fine. So an empty model, then, what that term means is no predictors. So it's a baseline for how you create an expected outcome for each person if you don't know anything else. So in this model, because the fixed intercept becomes the sample mean, because that's your best guess for what each person's outcome is if you don't know anything else, the E deviation from that sample mean for each person, if I take an E for each person and then calculate the variance across people, the number that I get back, such as the 190 here, is all the variance that there is in the outcome. So that's the starting point. And in this picture, the prediction given by the empty model is illustrated by the purple line that's flat. And so E would be how far off each of these little dots is from that purple line. So 190 then in this example outcome is all of the variability that there is in the sample for this variable. Now if we add a predictor, such as education centered at 12 in this example, the new expected outcome that's created by the model is shown by this blue regression line that has a positive slope. And indeed, the slope of the predictor worked out to be 1.8. So now the E that is left for the residual is the deviation of each of these little dots from the blue line. So if we look at what happened for this one person out here, this person has an actual outcome of 58.8, and relative to the empty model, the predicted outcome is closer. So the distance that's covered between the two lines in red here is no longer E, it's attributable to the model, whereas the remaining distance from the dot, or from the blue line up to the dot is still unexplained. So the total variability across everyone's E's is reduced to 162. So there is a homework question. I think there's two questions, as a matter of fact, about this idea. So I can look at these two numbers and say, all right, I started at 190 and I ended up at 162. Now, is that difference in the size of the residual variance significant? How do I know? Well, if I look at the difference between the models, I'll highlight them here. What's different between the two? The slope, beta 1. So if the addition to the model formed by beta 1 times that predictor is a significant slope, then by definition, there is less E variance left over than there was to start with. Because this is the only way the two models differ. So if this is a significant improvement to the prediction, that shows up as a significant reduction in residual variance. So there's less error around the mean than before because we're not giving everybody the same predicted outcome as the mean. We're giving them a conditional mean based on their education level. Now, if education was not a significant effect, if we looked at the coefficient for the slope and it corresponded to a p-value that was greater than alpha, then even though this number might be smaller, it's not significantly smaller. So because the difference in the models is entirely this beta 1 coefficient, the significance of that coefficient tells you whether or not the residual variance is reduced significantly as well. And that is true so long as you have only one thing that's different between these two models. That is no longer true once you have more than one thing, which is where we're headed this week and next week. Okay, so did that help answer the question about residuals?
Yes, thank you.
Okay. And keep in mind that when we're talking about e's, we usually talk about e's in squared form because the e's can be positive or negative and we don't want them to cancel. So variance is a squared number. The square root of that is standard deviation. Okay, other homework questions or things that would be helpful to review? I'll take that as a no then. Got radio silence, or is it, if it's not radio, right? It's like TV silence or something. Zoom silence? I'm not sure what the term is. Well, if you come up with a question after today, office hours this afternoon, both of my classes have homework due on Monday, so I might be a little bit busy, but I will try to accommodate as many folks as I can. And you can also email or visit the TAs as needed. So I will close that one then and head back over into lecture 3 then, if we're ready to get to some new stuff. That sound good? It's a rhetorical question, but you can still express enthusiasm, right? New stuff, yay! That's why we're here, right? New stuff. So we ended up, I think, on this slide here. So where I'm headed is models that take more than one slope to describe the effect of a predictor variable. So there's several situations in which the total effect of a predictor cannot be characterized by just one linear slope. We need multiple slopes. The first instance of this is when you have a categorical predictor that has more than two groups. So to review what happens when we have two groups, you have to set up a new predictor where one of the groups, so groups and categories are synonymous to me, by the way. I'm trying to say category, but groups is a lot more common, so it's the same. We set up a brand new predictor variable so that one of the groups has a value of 0 and the other group has a value of 1. It does not matter which we pick because the model will rearrange itself as needed to accommodate whichever group has a higher mean outcome. So if my model looks like this, for instance, then the intercept gives me the predicted mean for the group coded 0 because the intercept is always, always, always the predicted outcome when all of your X predictors are 0. So in this case, it's for the group who was coded 0. Then to get to the difference between the groups, that's where beta 1 comes in. So beta 1 for the effect of this 0, 1 categorical predictor tells you how different the group coded 1 is from the group coded 0. And I'm saying it that way on purpose because direction matters. If the group coded 1 has a higher mean in the outcome, then the slope will be positive. If the group coded 1 has a lower mean, the slope will be negative. So we know from the model directly, without having to ask for any information, what the mean for the group is coded 0 because that's beta 0. And we know what the group difference is between the group coded 1 and the group coded 0 because that's beta 1. So the slope is the change in y, the outcome, for a 1 unit change in x. In this context, that means we're going from the group coded 0 to the group coded 1 as a 1 unit change. So then the missing piece is, okay, so if I know what the group 0 mean is, and I know how the group 1 mean differs, what's the group 1 mean? And that's where we have to write one more line of code to get that additional piece of information. So it's beta 0 plus beta 1 times 1. So the value of the predictor for the one group is 1. And that linear combination right there gives us what the predicted mean is for the one group. So this special case of a general linear model when you have a binary predictor is otherwise known as a two-sample or independent groups t-test. And that's what you get a chance to practice on homework 2 in the last section. Okay, are we good with that much? Or any of that you want to hear again? Okay. So then how does this story have to change in order to accommodate a predictor variable that has 3 or more groups? That's where we're headed. So in general, your general linear model has to have as many fixed effects as you have categories for each category of your predictor to be given its own mean. So if I have 3 groups, then I start with beta 0 as one of the terms I need, and I need to fill in 2 more terms, 2 more fixed effects as slopes, because that will give me 2 of the possible group differences, and the others are all going to be linear combinations. Likewise, if I have 4 groups, I need to make 3 new predictor variables, give them each slopes, because then I'll have 1 intercept, 3 slopes, gets me to my 4 groups. And if I had 5 groups, I would need to make 4 new predictor variables, and then I'd have an intercept and 4 slopes to get me to my 5 groups. So you will see the word pairwise used in your textbook, and that's a word that I often use. Pairwise means between 2 groups. So the model gives you the difference between each pair of groups. The difference between each pair of groups will either be given directly as one of the slopes, or it will be given indirectly as a linear combination of the slopes. And so I want to teach you how to get it either way. And here's the formula by which you can figure out how many distinct pairwise group differences are possible. And the name that all of this logic goes by, the idea of having a categorical predictor of a quantitative outcome when there's 3 or more categories to the predictor, is analysis of variance. That's what this is called, or ANOVA. What we will come to see is that ANOVA is actually not a very useful name to describe this, because it's all about mean differences. It's not about variance. So it should be like ANOME instead of ANOVA, but people don't talk that way. But this is what it is referred to in an older traditional language, but it's all within the same modeling framework. This is just a special case with a special name. Okay, questions so far? So now the question is for us to decide as analysts, how am I going to set up the model to tell me what I want to know? So we have to do some coding with respect to creating these new predictor variables so that we get a reference group mean and mean differences of each other group relative to a reference group. So the term reference group is going to refer to which group is coded 0 across all of the predictors to be created so that the fixed intercept becomes its mean. So here's an example. I have a new variable to introduce from the General Social Survey, which is a self-reported question: do you view yourself as lower class, middle class, or upper class? And these are the categories that people chose. 436 people said they were lower class out of 734. 278 said they were middle class, and 20 people called themselves upper class. So unequal sample sizes across these 3 groups. Here is what I'm going to end up doing with my new predictor variables. I'm going to make one new variable that I have named L versus M, because what it is going to represent is the difference of low versus middle. So I've named them in a way that conveys what they represent to me. So the low group is going to be my reference group in this example. They are going to have their predicted mean given by the fixed intercept only. To make that happen, I zero them out across both of the new predictors to be created. And I need 2 predictors because I have 3 groups. We're going to do 4 groups next. So the first variable then, if somebody is in the middle group, I give them a 1 instead of a 0. So think of it like a switch. It's like a light switch. This is the variable that's going to activate the middle group. The upper group stays at 0 because it's not their turn yet. In the second variable to be created, the reference group of low still gets a 0, the middle group still gets a 0, and the upper group gets a 1 because this variable is for them. Is the line straight? I think I missed that question from probably a few minutes ago. What line? I apologize. When the low becomes the intercept. There's going to be two lines. And low is going to be at the 0 value of both of the lines. So I've got slopes coming on the next set of pictures. I just want to describe the logic of how these predictor variables are created to start with. Yeah, no problem. So when both of these predictors are included in the model at the same time is when this works. This will not work if I try to do just one or just the other. So if you look at how the groups are combined within the coding scheme, if I just had this column right here, L versus M in the model, then I am lumping together the low group and the upper group is the 0. So if this variable all by itself would tell me how the middle group differs from the average of low and upper. That's not what I want. So that's why I need the second variable to split apart the low and upper groups that were put together by the 0, and now they are distinguished in the second variable. So when all is said and done, this L versus M tells me how the middle group differs from low. The L versus U variable is going to tell me how the upper group differs from low. And middle versus upper is going to be a linear combination of those two. So the model will look like this. Reviewing terminology briefly, y sub I, what's that? That's my outcome. It's the original outcome. So y sub I is the column in your data set that corresponds to the variable to be predicted as the outcome, dependent variable, criterion, however you want to phrase it. So beta 0 is my fixed intercept. Always, 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 not only in this class, but in every class I teach, the fixed intercept is the expected outcome when all your predictors are 0. So given our coding scheme, both of these new predictors are 0 when I'm talking about the low group. That means that beta 0 will be the predicted y for my low group specifically. Then I have two predictors, L versus M and L versus U, and they have i's because these are variables. Each person has either a 0 or a 1 in these two variables based on which group they are a member of. And each of these two new predictor variables that I've created is going to be given its own slope. So I've got a beta 1 that goes with L versus M, and I've got a beta 2 that goes with L versus U. And then last but not least, normally colored blue, but apparently I missed it here, is our friend E sub I. What's that? Residual. Give me all the words in your head that go with residual. Otherwise known as errors. How far off from predicted? Leftover, yep. Unexplained, yep. I would say it's not variance because each person has a distinct E value. The variance of the E values is your residual variance. So E is like a representation that variance is a thing that we need to keep track of. I also would take discrepancy. Yep. So all of those words go together. So then the next equation that's down here starts off with something different, y hat. That's because it doesn't have an E. So the idea of y hat is, okay, what does the model say your outcome's supposed to be? I know that it's not going to be right, but what does the model say? So y hat is a placeholder for how this equation builds a custom created outcome for each person. So right now, because I only have 3 groups, there's only 3 possible outcomes, 1 for each group. As we add more predictors down the line, there's more possibilities for what y hat could be in a given data set based on whatever combinations of predictor values we've added. So then how does the model tell us what the predicted outcome is going to be for each group? So people talk about this in terms of the group means specifically. So you can say that y hat for a group is the predicted outcome mean for that group, or just predicted outcome. Either one of those is correct. So for the low group, let's fill in the values of the predictor variables that correspond to my coding scheme if you're in the first group for low. Well, at a minimum, every group gets a beta 0 to start with. Beta 1 is shut off at 0, because in my coding scheme, the low group is coded 0. Likewise, beta 2 shut off at 0. So the last 2 terms cancel, and we're left with just beta 0. So that's the first fixed effect, tells us the reference group mean for the group that's coded 0. Next one, middle and upper. Same exact process, now switching out the values of the 0s and 1s that correspond to the coding scheme for those 2 latter groups. So if I'm in the middle group, my predicted outcome is a linear combination of beta 0 plus beta 1. And if I'm in the upper group, my predicted outcome is a linear combination of beta 0 plus beta 2. So because these 2 quantities are combinations of your results, that's something you're going to have to ask for to get them to show up in your output. Betas that are part of the model show up by default. Linear combinations of betas to create model predicted outcomes for not reference groups are something you have to ask for. Okay, how are we doing? Okay, now if I have 3 groups, how many possible pairwise differences are there that I might be interested in? Well, I might want to know about low versus middle, that's 1. Low versus upper, that's 2. And also middle versus upper, that's 3. So there's 3 potential differences that I might want to talk about with respect to how this variable predicts my outcome. So 2 of them are given directly by the betas. So the logic here, the group that is after the versus is the comparison group. They come first. So the predicted outcome for the middle group is beta 0 plus beta 1. We figured that out up here. The predicted outcome for the low group is beta 0. The beta 0s cancel, and we're left with beta 1. So beta 1 all by itself already tells me how the middle group differs from the low group. Likewise, the upper group, its predicted outcome is beta 0 plus beta 2. We found that right here. The predicted outcome for the low group is beta 0 all by itself. The beta 0s cancel, and we're left with just beta 2. So beta 2 directly tells us how the upper group differs from low. The trickier one, middle versus upper. I don't have a variable that tells me that by itself, but the model does tell me it. So it would look like this. The mean for the upper group, beta 0 plus beta 2. The mean for the middle group is beta 0 plus beta 1. If I distribute the negative through, the beta 0s cancel, and I'm left with beta 2 minus beta 1 as the linear combination. So I can get my calculator out and figure out what that number should be. But my calculator can't as easily tell me what the standard error is for that new linear combination, and thus whether it would be significantly different than 0. So for those things, we need to ask for it. So to summarize then, there's 6 pieces of information that are relevant to fully describing how this outcome variable differs across my three groups. I want to know what is the predicted outcome in each of the three groups. That's three of them. And I also want to know how the predicted outcome differs between each pair of groups. That's the other three. 3 of the 6 are given directly as betas, and the other 3 are linear combinations of the betas. Okay, got numbers on the next slide, but before we do numbers, how are we doing? Okay so far? In general, under this type of coding scheme, which is called indicator coding, so there is a term for the process of giving group variables zeros and ones. It's called dummy coding. This is a specific flavor of dummy coding called indicator coding. And I'm using the terminology that's in your textbook. There is a very helpful table on page 278 that compares different coding schemes for predictor variables, and this is the one called indicator coding. Want to see some numbers? Okay. So I have results. I have estimates for each of the betas. I've got standard errors for each of the betas, and I've got residual variance for the model. All of that comes from SAS, Stata, or R. So after we're done going through sort of the logic of how you include predictor variables, I'll show you how you make the codes to actually get the numbers for yourself in a given data set. And you'll get a chance to practice this in homework 3. So empty model as a point of comparison. In this example, we're predicting income in thousands of dollars again. So the empty model with no predictors says if I don't know anything else about a person, my best guess for their predicted outcome is the mean, which is 17.3 in my sample. And residual variance across all of these individual e-residuals is 190. So 190 is all the variance that there is to be had in this outcome. The question is, by how much can I reduce it by including this predictor variable? So conceptually, the predictor is one idea. It's group membership. But in terms of the equation, group membership is represented by beta 1 and beta 2 to distinguish among the 3 groups. So in the solution, after I add these 2 new predictor variables that were created using this coding scheme of zeros and ones, beta 0 for my intercept worked out to be 13.65. The intercept is always, always, always the predicted outcome when your predictors are 0. So that's the mean for the low group given my coding scheme. Beta 1 is 8.85 according to these data. Beta 1 is a slope. All slopes are the change in the outcome for a 1-unit change in its predictor. A 1-unit change in the predictor that goes with beta 1 is this L versus M. It corresponds to going from a 0 to a 1. So putting that together, 8.85 is how much higher the income is for the people who said that they were middle class than the people who said that they were lower class. So $8,000 and some change. The estimate itself, the expected imprecision of it across samples is given by the standard error for the slope. So 1 is how far off on average that sample slope is expected to be from the population slope. If I take my estimate and divide by the standard error, I get a t of 8, meaning that this slope of 8 is like 8 standard errors away from the null hypothesis of 0. Very, very unlikely that I would end up with a slope of 8 if the true slope in the population were 0. That corresponds to super unlikely would happen less than 0.01% of the time. So this way of writing it describes a significant slope. P is less than 0.001, where significant is a label that we attach based on our a priori decision of alpha. So if it's less than 0.05 by convention, we call it significant. All right. Questions on that so far? Yeah?
So where 8.85 number comes from, is it the same data that
Yep, this is the same data set that I used in lecture 2.
Okay.
We're predicting annual income from the General Social Survey of 2012, and I have a subset of that data that are complete with respect to all the variables I'm actually going to end up showing you. So, yep, these are real data, even though it seems like that's a very low amount of income. I did not doctor the data. I did not change any of the values. It really is that low. I picked this variable because I was almost certain that it would be related to income, and I was right. So is this the most theoretically informative research question? No. But it works very well for a demonstration of math that has a giant signal to be detected. So people who said they are middle class are predicted to have greater income by $8.85 thousand, and that is significantly greater because it would happen less than 0.05, it would happen less than 5% of the time, put it that way. Then beta 2. So beta 2 swoops in to handle the comparison of the other non-reference group, which is the upper class group, relative to the lower group. So 10.98 is how the upper group differs on average from the lower group. And that has a standard error of 3. So 11 divided by 3 is somewhere less than 4-ish in my head. So like 4 standard errors away from the null hypothesis, still very unexpected. So the same conclusion, this is a significantly positive slope. People who labeled themselves upper class make significantly more money by 10.98. The residual variance then was estimated to be 1.71. So what that number refers to is for each individual person in this data set, I use this model to compute their predicted income based on their standing on this predictor variable. E, for each person, is how far off their real income still is from the one that's predicted by the model. So the variance of those E residual deviation leftover errors is 1.71. Now that's smaller. We got 190 versus 171. But in this case, I can't just look at the results of these two slopes and say whether or not this is significantly smaller. Because it could be because beta 1 matters, it could be because beta 2 matters, or it could be because they both matter. So it's ambiguous. But there is a way to answer the question more definitively that we'll talk about in probably next week. Odds are good. But if the model is useful in predicting income, the residual variance should be lower than what it was before, and indeed it is. Okay, now the fun part, differences in linear combinations. The model tells me what the middle group mean is predicted to be. I fill in the predicted, I create a predicted outcome using the betas that were obtained and the values of the variables for the predictors that multiply them. So 13.65 is what beta 0 was estimated to be. 8.85 is what beta 1 was estimated to be. If I'm predicting the mean for the middle group, then L versus M turns onto a 1. 10.98 is what beta 2 was predicted to be, but in that variable, the middle group is coded 0. Right here, that one. So if I do the math to work this through, I end up with a prediction of 22.5. So this one I have to ask for as a linear combination because it involves more than one beta. Likewise, for the upper group, same exact beta coefficients, but then different zeros and ones based on what it is for the upper group. And theirs is 24. The remaining group difference then, I can look at these two means and tell you how they're different. Well, it looks like the upper group is bigger by 2, but to get a test of that, I need to ask it to take beta 2 and subtract beta 1, and that works out to be 2.13 specifically, but the standard error is 3. So do you remember standard errors? What they tell you for a slope? Expected inconsistency. So in other words, for this comparison, which represents how much more money the upper class people make than the middle class people, again, this is all self-reported, as they assign themselves to these groups. On average, a slope that captures that group difference is going to vary from the population slope by 3. Our slope was only 2. So a slope of 2, given an expected inconsistency of 3, is well within expected fluctuation. 2 is not different than 0. It would happen within 95% of the time. And actually, the exact p-value for it is 0.48. We would see a slope this big of 2, given an expected inconsistency of 3, like 48% of the time. So this one's not significant, unlike the other two. Any guesses as to why the standard error for middle versus upper is so large relative to the standard errors for the others? Sample size, yeah. So if you look at this page here, any standard error that has to do with the upper group is bigger than all the others because they have 20 people. So we really don't have a good, reliable, consistent estimate of what the mean is in the upper group because I only have 20 people relative to 436 and relative to 278. So there's more expected inconsistency, which makes it harder to be able to say, yes, this group is different, because we don't really have a good sense of what the group mean is with only 20 people. In other words, any comparison involving this upper group is going to have less power because I only have 20 people. I have less of a chance of finding an effect that's really there the fewer people I have. Okay. How are we doing? Question?
Can you repeat the last sentence?
Yes. I have less of a chance of finding an effect that's really there if I have fewer people to find it with.
No, I mean the 2.13, and then we
Oh,
have like
the interpretation that goes with these numbers? Yep, okay. So the difference of how the upper group differs in income from the middle group is 2.13. That's what the model says it is. However, the model also says that the expected inconsistency of that difference is 3.03 across samples. So if I do 2.13 divided by 3.03, that gives me my t. It's going to be less than 1. And a t of 2-ish is generally the boundaries of where 5% starts for unexpected. So we would see a slope of 2 or greater, or a slope that is -2 or less, basically something that's more extreme in terms of being away from the middle, 48% of the time. Well within expected sampling fluctuation, not different than 0. Retain the null hypothesis, or do not reject. This is a positive slope, but it's not significantly positive. Unlike the other two.
You're saying that you can distinguish between the low and the middle.
Yep.
Your model will do that, and the low and the high, the upper, not between the middle and the upper, because the slopes are basically too close.
Yep.
For the number of people that we have.
Yep. So he said we can distinguish between the low and the middle. And yes, because beta 1, right here, we can distinguish between low and upper because beta 2. We cannot distinguish between middle and upper because beta 2 minus beta 1 is too close to 0. Yeah.
Can you remind me how you divide lower, middle, and upper group?
How we divide them?
Yeah, how you divide like 436.
Well, these are the frequencies within each category. So there's 734 people in the data set. Of those 734, 406 called themselves lower class, 278 called themselves middle class, and 20 people called themselves upper class.
So it's like self-report?
It's self-report,
Oh,
yeah.
oh,
Yeah,
thank you.
that was a question. Which are you? And this is the box they checked. Yep. So people who reported themselves as upper class are much less frequent, and they do make more money. It's just that we can't say they make significantly more than middle class. So putting it all together, the lower class people are sort of the ones that are more different than the other two. Middle and upper are less distinguishable, not significantly so. Yeah, pictures. Want to see pictures? Does that make it better? Maybe? It can't make it worse, right? Never say famous last words, because they could be. So I put this into Excel to try and give a graphical illustration of what's happening here. So the y-axis is my outcome variable that is being predicted by the model, which is annual income. And the x-axis actually has two different x-axes working in this picture. One of the x-axes is L versus M, which is 0 versus 1, and the other is L versus U, which is 0 versus 1. So this dot right here is the predicted outcome when both of my x-axes are 0. That's given by my intercept. So beta 0 of 13.65 is right here. Then the slope that talks about how the middle group differs from the lower group, which is beta 1, is given by the slope of this red line right here. So the change in y for a 1 unit change in x, or rise over run, that slope is 8.854. So that gets me to a mean for the middle group of 22.5. So it's 13.65 plus 8.854 gets me here. Likewise, the slope for lower versus upper is still a 1 unit change on that axis. The slope difference in that case is 10.985. So if I start with 13, add the 10, I get to the 24. So the one that we're missing is this increment between the blue and the red right here. That's the difference in y between middle and upper. And that's given by a linear combination of beta 2 for the blue triangle minus beta 1 for the red triangle, and that results in a 2. Question?
Maybe.
Maybe.
I don't know. You have the distance on basically the y-axis there is 2.13, but do you really want the slope between the 22.5 and the 24.63, which would be that over 1, which is essentially the same number? Is that really what you want? Like if there were a line from the 22.5 to there.
Yeah, that would work
and then
too.
you're just saying that that's not steep enough to be away from 0 that we can really say that it's anything.
Yeah, you could also draw a line from here to here. It's just that these are not on the same, like, it's two different x-axes to make the picture work. But this remaining discrepancy in the predicted y works out to be the same thing as the slope linking these two lines right here.
Yeah.
Okay. Did that answer your question?
It does.
Okay.
But it just, to me, it's weird because that's a change in y and not a slope. Where the other blue line is slope.
Well, the slope is a change in y for a 1 unit change in x. It's just that a unit is sort of a loosey-goosey concept.
Our x-axis is
Yeah. Yeah, this is not 0, 1, 2. But that actually brings up a really important point. What would happen if I put in the original predictor variable that was coded like 1, 2, 3 as one slope? The slope would try to give me the change going between lower and middle and upper, and it would constrain those two changes to be the same because it would be linear. So this is something that I see folks do as an early mistake is to not recognize that this variable that we're using as the basis of our x-axis is not numbers. They're categories. And if you try to put it into a stats package as a predictor that is numbers, it will run just fine, but it will give you garbage, because it will talk about the change if you go from group 1 to group 2 has to be equal to the change as you go from group 2 to group 3, because it's a linear slope. And that is clearly not the case here. There's a much bigger change if you go from group 1 to 2 than if you go from 2 to 3. Yeah, not better. All right, how are we doing? So let me take an informal poll here. Do you want to see how to get these numbers out of software next, or do you want to see what this would look like for 4 groups next?
Is this similar to 3 groups?
It's similar, but more complicated. Got 1 vote for software. A few more votes for software. Okay, 3 yeses and a whole bunch of abstains. Software it is. Let me get that handout up. Example 3 is what I need to get out. Because understanding how to do all of this is a necessary but not sufficient skill for actually being able to do all of this. The software part is always an additional hurdle to clear. So I'm at example 3, which is on the course webpage next to lecture 3. So let me pull that back up just in case. It was posted for Tuesday. I've got lecture 3 here, and example 3 is the handout that's going with it. And all of the files with respect to data, syntax, and output are inside this zip folder right here that I made the handout using. And of course, I finally see typos when it's, on a giant screen in front of me that I did not see before. But that happens. Okay. Ready to look at this? Sure. So first step, always tell your program where your data are and import it. So we'll go through SAS and then Stata and then R. This is the same GSS example data set that we used for example 2. So in SAS, the way you tell it where your stuff is this file save option right here. Note this piece. So that prefix is necessary if you are using the virtual desktop and you're using a place that is not the H drive. If you wanted to access your local machine, we need to have this part in front of it, and that thing also is a $sign when you copy it out of the path of Windows Explorer that needs to change to a colon. From there, then it accesses that place right here. This is the name of the file to be imported. It is going into SAS in the work temporary directory, and it is to be called example 3. And since it's Excel and you can have more than one worksheet inside a workbook, I'm telling it which sheet specifically that I want to have. And keep in mind, anything in this purple color is case and space sensitive, so it does have to be spelled exactly right for this to work. Then here are the labels for the variables we're going to be working with. So work class is the original name of the variable that has lower, middle, and upper as specific versions. So work class is the original column. We're going to have to make new columns out of that old column. Later in this example, we will have years of age. We'll have years of education come back. We'll also have happiness come back as something we've looked at before, and then income is the outcome variable. And I am selecting cases that have complete data with respect to all of those using the number missing function in SAS. This is not something you have to worry about in your homework. It is something you'll have to think about in life. So, any questions on the SAS code? All right, Stata folks. I have a slightly different version of importing from Stata that uses the same file save thing. The alternative is just to use the working directory CD, but I wanted to show you what it looks like if you want to define multiple places as multiple potential working directories at the same time. So I am defining a global variable called file save in stata that is going to hold this path as its contents. And that means that I can have multiple instances of these. So I can have a file save 1, file save 2, like I can pull things in and out of different places by referring to this as an abbreviation in the code. So it's like a working directory if you only have one, but it allows you to have more than one place active in Stata's memory at the same time. So import Excel then is going to make use of that abbreviation right here. So the $ and then file save ties it to look in this spot for the Excel file to be imported. If you set a working directory, you wouldn't need to have this front part because there's only one working directory indicated by Stata. Case means if it's capital or lowercase, leave it as it is. First row means import the data names, and clear means if I've already done this, go ahead and write over it. And then here are the variable labels that go with those things as well. And then row miss is the analog to selecting cases that are complete. Egen, by the way, is another way of making new variables that requires more complex functions. So gen works for most things. Egen works for special things, such as the use of this row miss function right here. So any questions from Stata folks on data import? Okay. All right, folks. I have setting the working directory. So this is on my local machine, not using virtual desktop. So it's exactly what it would look like inside Windows, except for the slashes are backwards. And I am using a read Excel package to import the Excel sheet. If you run this code, by the way, and you get an error, what have you possibly done wrong? What if it says, I don't know what read Excel is? In angry red font. Yeah, you haven't loaded your package. So what's not in the handout that is in the example files online is a whole thing that says, install this package if you don't have it already and load it. Install this package if you don't have anything already and load it. You have to run that part first.
You have to run that every time you open the program?
Yep.
Or just once?
Every time. It only installs it once, but the code that I have checks to see if it's installed and installs it if it doesn't. Because that way, if you're using a different machine than you used last time, you don't have to worry about that. But you do have to load the packages. So always running from the top of the file down is essential in all the programs. And then setting it up as a data frame, because sometimes files are imported as different types, and in most cases, they have to be a data frame for you to do any kind of analysis on. And R doesn't like variable labels for certain routines, and so I have them in comments inside the example files. Okay. Any questions from R users? Okay. First step always in doing any kind of data analysis, data description. Figure out what kind of variables you have, what kind of ranges they have, and in the case of trying to figure out coding schemes, you need to know how many different categories you have for your categorical predictors. So first up is quantitative and ordinal variables I am getting summaries for. So if I know that my variables to be summarized univariately are either quantitative or they're ordinal, and I'm going to pretend like they're quantitative, then I can do proc means in SAS, I can do summarize in Stata, and I can do the describe function inside the psych package to get that information. So this is what you got a chance to practice on homework 1, just getting basic descriptive statistics for these types of variables. So we have income, there's our mean of 17.3. That's going to show up as the prediction from the empty model. Standard deviation around it, if I square that, that's going to be my variance, the residual variance of the empty model, and there's the range of possibilities. Age and education are we're not going to look at today, but those are in there for future reference, same as happy. And then for categorical predictors. So if I have a predictor that has more than 2 groups, none of this is informative. If you have a variable that is nominal, something like low, middle, and upper class is the way we're treating it as nominal, then having the mean won't tell you anything. What we want to know is the frequency and how many distinct categories we have. So prop freq is how we ask for descriptive information from categorical variables. It's also tabulate in Stata, and the prop table command with table embedded in it is how we get the same thing out of R. So we're asking for these summary frequencies and proportions for working class, which is going to be a predictor in this example, and then also for a 5-category happy variable that will show up subsequently. So those are the 2 tables produced in SAS that tells us how many people are in each category, as well as how many categories there are in total. So then to represent working class, because I have 3 categories, I know I'm going to need 2 slopes. To represent happiness, if I don't want to treat these as numbers because they correspond to categorical labels, I know I'm going to need 4 slopes because there's 5 possibilities. But today we're just doing working class. Okay. Next step. I cannot take this working class variable and put it to the model as is. If I try to put working class into the model as is, what I will get back is a single linear slope that gives me the expected difference in my outcome variable between 1 and 2 and assumes the same difference between 2 and 3. These are not numbers, so we can't treat them as numbers. That's why we have to do the indicator dummy coding to create new predictors that we can treat as numbers, because their only possible values will be either 0 or 1. So we're creating new columns that we're going to use in the model in place of this original working class variable that's coded 1, 2, 3. First up, doing it in SAS. Note the sandwich here. So SAS users, anytime you want to make a new variable, you have to do it inside a command that tells it which data set you're talking about. So data and set to open it up, and run to close it. If you don't have those pieces, SAS will not understand what you're trying to do. This combination of listing the same data set in both places means save as itself. It's going to go bring up the example 3 data set, make these changes to it, and then save it under the same name. This is a step that's not necessary in Stata, because in Stata you only have one data set open in working memory at the same time. So first thing, this is code that you saw before. So in your homework, I asked you to create a dummy-coded predictor for age 3 versus 4. So this is related to that, except that it has more code because now I have to make 2 new predictors, not just 1. First step is making 2 empty columns. See if I can get it. I can almost get it all on one screen. There in Stata, and there in R. There we go. That one, and there we go. That. All of those happen, that they're doing the same thing. I'm creating 2 new columns, and I'm saying fill them with dots, which is program for missing. In R, it's the letters NA, capital letters, and they'll turn blue. So 2 new columns that are going to hold my 0s and 1s, opening them and setting them to be empty. then I am going to systematically fill those two new empty columns with zeros and ones that correspond to my coding scheme. So my coding scheme that the code is trying to execute is summarized in this table right here. This is what I'm trying to do. So I highly recommend that you have either a table in Excel or a piece of paper, like where you scratch this out, because it will help you to write the code that corresponds to this as the end goal. So first up in SAS, we're using conditional logic. So the words that it has here is almost literally what is happening. If the original variable is called work class equals 1, so 4 cases that are in the low group do this stuff, then do. My first new variable is going to turn to 0. My second new variable is also going to turn to 0, and that gets me the first row of this table right here. So again, L versus M and L versus U are the new variables that are being created by this process. The current existing variable is work class. And I have called these variables L versus M and L versus U because that's what I'm trying to code. I would encourage you to make names that mean something to you in the context of what you're doing. So I wouldn't ever call this L versus M if L versus M wasn't part of the story that I was trying to create a variable for. These variables can be anything that you want so long as they don't start with a number, and the only special character you're allowed is underscore. I think in R you can have periods too, but SAS doesn't like that, so I don't ever use periods. So this piece right here then is getting the first row of the table. The second row of the table is happening for the second line, and the third row of the table is happening for the third line. So if you've done this correctly, you should have only one 1 in each of the new variables, because in this coding scheme, the 1 activates that variable for the non-reference group. So for middle for the first one, for upper for the second. And then I added labels because I want to remind myself what I did later on. And note all the semicolons, SAS users. Seriously, a semicolon, that's what SAS stands for. There's one here that closes the do. There's one after each of the new variables, and then there's one after the end. So if you're typing this and the colors don't look right, check for missing semicolons. So when this is all said and done, you will have an original work class column of 1, 2s, and 3s, and you'll have 2 new columns in your data set of L versus M and L versus U. All right, questions on that? Okay, Stata folks, exact same thing, but written in the opposite order. So the command, first we start with 2 empty variables, and then we replace the first one that's empty with a value of 0 if we're talking about the low group, which is when work class is 1. So note the double equals here. That's an equivalence condition that it's evaluating. So if it's 1, then set the first variable equal to 0. And the second line does the same thing. If it's 1, then set the second variable equal to 0 also. And that gets me the first row of the table. These 2 commands in Stata get me the second row of the table of 1 and 0. And then the last 2 get me the third row. So it's replace new if old with respect to the names of the variables, whereas in SAS, it's if old, then replace new. So same idea, just a different way of saying it. And in R, of course, it's yet a third way. So this is the new variable to be created in R. It's in the example 3 data set. And it is eventually going to be 0 if the condition inside the brackets is met. So new variable, which old variable equals 1, new variable equals 0. And I don't know why sometimes it's blue and sometimes it's not. But it should hopefully all be blue for you inside RStudio. So that first 2 lines here get me the first row of the table. The second 2 lines get me the second row of the table. And then the third set of lines get me the third row. And now I'm ready to put them in a model. All right. Our users, any questions on how to go through and make these new variables? In all 3 of the packages, I would highly recommend after you run the code and it doesn't generate any error messages, to physically open up your data set and eyeball it. Because you will see whether you have zeros and ones or whether you have dots or something else went wrong. The things that people do by accident during this process that screw things up is to recode the old variable into a different value. So if you accidentally write over working class, then you can re-import your data from the start and get back to where you were. There's always a back door. Okay, 309, my goodness. Time flies when you're looking at code, doesn't it? Said no one ever, except me. But I did pick this for my job, so not randomly assigned to the code. I like it whenever dollar signs show up in code, because that just reminds me that if you learn this, someone will pay you so that they don't have to. Right? There's a lot of things in our economy where we pay people to do things that we don't want to. I pay the plumber to come unclog a toilet. I pay H&R Block to do my taxes. Right? Someone pays me to make R do things for them so that they don't have to run it. And eventually, someone will pay each of you. So here's my model then. So note, working class, the original variable is not in my equations and it's not going to be in my code. Working class as the original 1, 2, 3 predictor variable has served its purpose, it's done. It is to be replaced by these 2 new 0, 1 indicator dummy variables that we just created. So these equations are stolen directly from the PowerPoint slides, reminding you how the model tells us what the predicted outcome should be for each group based on our codings of zeros and ones across my 2 new predictor variables, and how well the model tells us what the group differences should be. So the model directly tells us all differences related to the reference group. Differences between the non-reference groups are the ones that are always going to be linear combinations. So because we set this up so that low is the reference, everything that is going to be in the model output is relative to low. Anything else that's mid versus upper is something we're going to have to ask for separately. All right. I think now is probably a good place to stop. And we can look at what happens in the model next time. All right, questions before we call it a day? Nope, we've had it. It's 3:12 in the afternoon and I'm done. Well, for those of you who still have to go to class or teach or parent, we're not done. I hope the rest of it goes well. For those of you who are truly done for the day, hope you enjoy yourselves. Homework's due Monday. Let me know if you need anything. Otherwise, have a good weekend. We'll see you next week. Thanks for being here. Thank you.